Back in the last century, it was truly a golden age of human space exploration. As our understanding of the universe grew, it became increasingly clear just how tiny we really are. Even our solar system is nothing more than a humble planetary system within the Milky Way. What you're looking at now is the massive disc-shaped structure we call the Milky Way, an enormous collective made up of countless stars. It contains at least 200 billion stars, most of which are concentrated within 4 major spiral arms. According to the latest astronomical data, the Milky Way is roughly 160,000 light-years in diameter, and our solar system lies within the Orion Arm, about 26,000 light-years from its center. At this very moment, the Sun, along with all the planets in our solar system, is traveling around the center of the galaxy at roughly 230 kilometers per second. It takes about 220 million years to complete a single orbit. So, with a galaxy this immense, is it even possible for humanity to leave it? We do have one spacecraft that has traveled farther than any other, NASA's Voyager 1, launched back in 1977. It has been drifting through the darkness of space for over 40 years, and it is now roughly 22 billion kilometers from Earth, roughly 20 times the distance of one light day. At its current speed, it would take about 17,000 years just to completely leave the boundaries of the solar system. Meanwhile, the Milky Way itself spans 160,000 light-years across, with an average thickness of roughly 3,000 light-years. Even if Voyager 1 were to travel straight upward, perpendicular to the disk, it would take roughly 52.8 million years to break free of the galaxy dot. However, Voyager 1 is currently moving at only about 17 kilometers per second, far too slow to ever break free from the Milky Way. To escape the galaxy, a spacecraft must first achieve what's called the 4th cosmic velocity. This is the minimum speed required for an object launched from Earth to overcome the Milky Way's gravity. According to the latest calculations of the galaxy's total mass, the escape velocity of the Milky Way is roughly 550 kilometers per second. In other words, only at this speed can a spacecraft break away from the galaxy. But even then, it would take millions of years to make the journey. Clearly, for a human lifespan measured in mere decades, this is meaningless. At this point, many people might wonder, what if we could travel at a speed infinitely close to the speed of light? According to Einstein's theory of time dilation, as an object approaches the speed of light, time slows down drastically for that object. In theory, this would allow us to cover light-year distances within a manageable span of time. However, reality is far less forgiving. As an object's speed increases, its mass also increases, and it requires an enormous amount of energy to sustain that speed, far more than any human body can tolerate. So, the best hope for leaving the Milky Way doesn't lie in brute force speed, but in bending space-time itself. Concepts like wormholes, shortcuts that connect to distant points of space-time, or warp drives, which compress space in front of a spacecraft and expand it behind, could one day enable faster-than-light travel. Yet, as of now, our understanding of these ideas is virtually non-existent. Some physicists even estimate that sustaining a warp drive would require more energy than the universe itself contains. In short, if we ever hope to venture beyond the boundaries of the Milky Way, it may still be far, far in the future. If we ask which planet is the largest in our solar system, the answer is undoubtedly Jupiter. Not only is it incredibly massive, but it's also immense in size, large enough to hold 1,321 Earths, within its volume. Its mass is roughly 2.5 times that of all the other planets combined, making it the undisputed giant of the solar system. As a gas giant, Jupiter is very similar to the Sun. Its composition is mostly hydrogen, making up about 75% of its bulk, with roughly 24% being helium. This is why many people wonder, if Jupiter is made of almost the same ingredients as the Sun, what would happen if a huge meteor crashed into its surface? Could it ignite the planet and turn it into a shining star? To understand this question, we first have to review how the Sun itself shines. The reason the Sun shines and gives off heat is due to a process called nuclear fusion deep within its core. Here, 4 hydrogen atoms fuse together to form a helium atom, releasing an enormous amount of energy. This reaction is sustained by unimaginable conditions, roughly 300 billion times the pressure of Earth's atmosphere and temperatures of about 15 million degrees Celsius. Thanks to the Sun's immense gravity, its core maintains these extreme temperatures and pressures, allowing hydrogen to burn steadily and reliably. By contrast, Jupiter is nowhere near that level. Its core pressure is only about 40 million times that of Earth's atmosphere, and its temperature is roughly 30,000 degrees Celsius, far too low for hydrogen fusion to occur. So, even if a massive meteor crashed into Jupiter, it would only release a burst of energy upon impact. It wouldn't ignite hydrogen or sustain a fusion reaction. In fact, this was demonstrated in 1994, when comet Shoemaker-Levy 9 was torn into 21 fragments by Jupiter's gravity. These pieces slammed into the planet's southern hemisphere at speeds of about 60 kilometers per second, releasing energy roughly equal to 40 trillion tons of TNT, the equivalent of 20 trillion Hiroshima bombs. Yet, despite this cataclysmic collision, Jupiter remained unchanged, and its hydrogen never began a fusion reaction. Theoretically, there is only one way for Jupiter to become a star. Astronomers have calculated that stars have a minimum mass threshold, roughly 7 to 8% of the Sun's mass for hydrogen fusion to occur. Currently, Jupiter has only about 0.1% of the Sun's mass. In other words, it would need to gain roughly 80 times its current mass for its core to reach the pressure and temperature required for fusion. Only then could Jupiter evolve from a gas giant into a faint, glowing red dwarf. Unfortunately, this is virtually impossible. The Sun contains about 99.86% of all the mass in the solar system. Even if we somehow hurled every planet, asteroid, and comet into Jupiter, its total mass would still be nowhere near enough to ignite as a star. Humankind has always been a species driven by curiosity and exploration, ever since the Soviet Union launched Sputnik 1 in 1957, the first artificial satellite. We have been reaching out into space. As technology progressed, our gaze shifted toward the closest celestial body, the Moon. In 1969, the United States launched Apollo 11, carrying 3 astronauts on a historic mission to land on the Moon. Neil Armstrong became the first human to set foot on its surface. And although mankind has yet to venture beyond the Moon in person, our spacecraft have traveled far deeper into space. On September 5, 1977, Voyager 1 was launched. It flew past Saturn and Jupiter, using their gravity to slingshot itself to the 3rd cosmic velocity. Today, it has reached the very edge of our solar system. Yet even this reminds us of how tiny the solar system really is. A mere speck in the vast expanse of the universe, far beyond our Sun. Countless other planetary systems fill the galaxy. At the speed of light, It would take 4.22 years just to reach the nearest star, Proxima Centauri. Even with the fastest spacecraft we have today, it would still take tens of thousands of years to make the journey. If we traveled 200,000 light-years from Earth at the speed of light, we'd find ourselves within a massive spiral galaxy called the Milky Way. This galaxy contains at least 200 billion stars, and our solar system rests within its Orion arm, roughly 26,000 light-years from its center. A complete orbit of the galactic core takes roughly 250 million years. If we kept going and flew 13 million light-years from Earth, we would find ourselves in an even larger cosmic structure, the Virgo supercluster. This colossal grouping contains over 2,500 galaxies, including the Milky Way, and if we pushed further still, reaching 13.7 billion light-years from Earth, we'd witness the sprawling cosmic web, a lattice of galaxies and superclusters. Each point of light would be an enormous supercluster of galaxies. In the observable universe alone, scientists estimate there are at least 200 billion galaxies. Based on its expansion and the measured recession of galaxies, the universe is estimated to have a radius of roughly 46.5 billion light-years, yielding a total diameter of about 93 billion light-years. Yet this is only what we can observe. What lies beyond this boundary remains a complete mystery. Perhaps other universes are out there, hidden in the depths of the infinite void. Asterisk. In the vast expanse of the universe, our planet, and all of us, are but a tiny whisper. Although we are almost insignificant in the grand scheme of the universe, we continue to follow in the footsteps of those who came before, venturing into places no one has ever set foot. Long before the time of Einstein, physicists believed that light traveled through an invisible medium called the ether. They spent countless hours searching for evidence of its existence. In 1887, Albert Michelson and Edward Morley conducted a famous experiment to measure the speed of the Earth as it moved through this ether. The goal was to detect differences in the speed of light in different directions. According to Galileo's theory of velocity, physicists expected to find two different speeds of light. But the results were shocking. The speed of light was found to be the same in every direction and in every inertial frame of reference. This discovery became known as the Michelson-Morley experiment, and it laid the groundwork for one of the core tenets of physics, the invariance of the speed of light. This finding had a profound influence on Einstein, shaping the development of special relativity. Einstein proposed that as an object with rest mass accelerates closer to the speed of light, its mass increases, requiring more and more energy. To actually reach the speed of light, an object would require infinite energy, making it an unattainable limit for anything with rest mass. Hence, Einstein concluded that the speed of light is the speed limit of our universe. Yet, this statement is often misunderstood. The fact that nothing can travel faster than the speed of light applies only to objects with rest mass, to matter and information. The expansion of the universe itself, as well as the phenomenon of quantum entanglement, can appear to operate beyond the speed of light, but neither contradict relativity. Why? Because cosmic expansion is the stretching of space itself and doesn't carry information from one point to another. Meanwhile, quantum entanglement, despite its instantaneous nature, doesn't allow for the transmission of information. In other words, the speed of light is a limit for matter and information, not for space or quantum connections. In essence, the speed of light is the ultimate speed limit for matter and information in the universe, but not for space itself, nor for the strange links that connect particles across the quantum realm.